So I'm going to go through the read aloud pages from our textbook that we're going to either listen to this or read it on your own and take notes in class in your notebook. So we started the week looking at physical and chemical properties of matter. We're going to switch over now and take a closer look at physical and chemical changes and how you can tell the difference. And that's what this reading will outline here too. I'm just going to go ahead and read aloud, and you can follow along. And as you hear things that might be of importance, for example, a definition or an example, that would be a good time to press pause and jot those down as notes in your notebook that we're going to use at some point for quizzes and tests and stuff to help you. So as you can see over here, what we'll learn, comparing several physical and chemical changes and being able to identify examples of those changes. And these three terms right here over on the side for vocab, those are kind of our biggies for this whole unit. And when we get to our test in 3-4 weeks here, that's going to be the most important things or the concepts for this. So, all right, physical changes. What happens when an artist turns a lump of clay, shown in figure 7, into a work of art? The composition of the clay does not change. Its appearance, however, changes dramatically. The change from a lump of clay to a work of art is a physical change. A physical change is one in which the form or appearance of matter changes, but not its composition. So it just looks different. It's not made up of different things after the change. The lake in figure 7 also experiences a physical change. Although the water changes state due to a change in temperature, it's still made of the elements hydrogen and oxygen. Changing shape. Have you ever crumpled a sheet of paper into a ball? If so, you caused a physical change. Whether it exists as one flat sheet or a crumpled ball, the matter is still paper. Similarly, if you cut fruit into pieces and you make a fruit salad, you do not change the composition of the fruit, you change only its form. Generally, whenever you cut, tear, grind, or bend matter, you're causing a physical change. So these pictures that it was referring to in figure 7. Dissolving. What type of change occurs when you add sugar to iced tea, as shown in figure 8? Although the sugar seems to disappear, it does not. Instead, the sugar dissolves. When this happens, the particles of sugar spread out in the liquid. The composition of the sugar stays the same, which is why the iced tea tastes sweet. Only the form of the sugar has changed. It shows here that the sugar blending into the iced tea is actually an example of a physical change. Changing states. Another common physical change occurs when matter changes from one state to another. When an ice cube melts, it becomes liquid water. The solid ice and the liquid water have the same composition. It's only in a different form. Matter can change from any state to another. Freezing is the opposite of melting. During freezing, the liquid changes to a solid. A liquid can also change to a gas. This process is known as vaporization. During the reverse process, called condensation, the gas changes to a liquid. Figure 9 summarizes these changes. In some cases, matter changes between the solid and gas states without even becoming a liquid. This process, which a solid changes directly to a gas, is called sublimation. The opposite process, in which a gas changes to a solid, is called deposition. Chemical changes. It's the 4th of July in New York City, and brilliant fireworks are exploding in the night sky. When you look at fireworks, such as these in figure 10, you see dazzling sparkles of red and white trickle down in all directions. The explosion of fireworks is an example of a chemical change. During a chemical change, substances are changed into a different substance. In other words, the composition of the substance changes. You are familiar with another chemical change. If you've ever left your bicycle out in the rain, after a while a small chip in the paint leads to an area of reddish, powdery substance. This substance is rust. When iron and steel is exposed to oxygen and water and air, iron and oxygen atoms combine to form the principal component in rust. In a similar way, coins tarnish when they're exposed to air. These chemical changes are shown in Figure 11. And kind of the before and after, those are all definitely chemical changes, or the rusting of things and tarnishing of things. The brilliant colors of autumn result from a chemical change. What are some signs of a chemical change? You can't see the colors here on the trees necessarily, but it's just showing the difference between, green tree and definitely as it changes colors, it loses that green and changes colors, and eventually those fall from the tree. So physical changes are relatively easy to identify. If only the form of a substance changes, you've observed physical change. How can you tell whether a change is chemical or physical? If you think you are unfamiliar with chemical changes, think again. You've witnessed a particular change if you've seen the leaves of trees change colors in autumn, but you are not seeing a chemical change. Chemicals, called pigments, give trees their color. In Figure 12, the pigment that is responsible for the green color you see is chlorophyll. Two other pigments result in the colors you see in the red tree. Throughout the spring and summer, chlorophyll is present in much greater amounts than these other pigments, so you see it as green. In autumn, however, changes in temperature and rainfall amounts cause trees to stop producing chlorophyll. The chlorophyll that is already present undergoes a chemical change in which it loses its green color. Without chlorophyll, the red and yellow pigments, which are always there, can be seen. Perhaps you have found that a half-eaten apple turns brown. The reason is that a chemical change occurs when food spoils. Maybe you have toasted a marshmallow or a slice of bread or watched them turn black. In each case, the color of the food changes as it's cooked because a chemical change occurs. Energy. Another sign of a chemical change is the release or gain of energy by an object. Many substances must absorb energy in order to undergo a chemical change. For example, energy is absorbed during the chemical changes involved in cooking. When you bake a cake or make pancakes, energy is absorbed by the batter as it changes from a runny mix into what you see in Figure 13. Another chemical change in which a substance absorbs energy occurs during the production of cement. This process begins with the heating of limestone. Ordinarily, limestone will remain unchanged for centuries. When it absorbs energy during heating, it undergoes a chemical change in which it turns into lime and carbon dioxide. Energy also can be released during a chemical change. The fireworks you read about earlier released energy in the form of light that you can see. As shown in Figure 14a, a chemical change within a firefly releases energy in the form of light. Fuel burned in the camping stove, shown in Figure 14b, releases energy you see as light and feel as heat. You also see that energy is released when sodium and chlorine are combined and ignited in Figure 14c. During this chemical change, the original substances change into sodium chloride, which is ordinary table salt. Here's your, it says in Picture A, energy is released when the firefly glows, when fuel is burned, like in a camping stove, and when sodium and chlorine undergo a change to make table salt. Pretty cool. Odor. It takes only one experience with a rotten egg to learn that they smell much different than fresh eggs. When eggs and other foods spoil, they undergo chemical change. The change in odor is a clue to the chemical change. This clue can be used to save lives. When you smell an odd odor in foods such as chicken or pork or mayonnaise, you know the food has undergone a chemical change. You can use this clue to avoid eating spoiled food and protect yourself from becoming ill. Gases or solids? Look at the antacid tablet in Figure 15a. You can produce similar bubbles if you pour vinegar on baking soda. The formation of gas is a clue to a chemical change. What other products undergo chemical changes and produce bubbles? Figure 15b shows another clue to a chemical change, the formation of a solid. A solid that separates out of a solution during a chemical change is called a precipitate. The precipitate in the photograph forms when a solution containing sodium iodide is mixed with a solution containing lead nitrate. Not easily reversed. How do physical and chemical changes differ from one another? Think about ice for a minute. After solid ice melts into liquid water, it can refreeze into solid ice if the temperature drops enough. Freezing and melting are physical changes. The substances produced during a chemical change cannot be changed back into the original substances by physical means. For example, wood changes into ashes and gases that are released into the air. After wood is burned, it cannot be restored to its original form as a log. Think about a few of the chemical changes you just read about, and see if this holds true. An antacid tablet cannot be restored to its original form after being dropped in the water. Rotten eggs cannot be made fresh again, and pancakes cannot be turned back into batter. The substances that existed before the chemical change no longer exist. This stuff. Chemical versus physical change. Now that you've learned about many of the different physical and chemical changes, you have read about several characteristics that you can use to distinguish between physical and chemical changes. The most important point for you to remember is that in a physical change, the composition of a substance does not change, and in a chemical change, the composition of a substance does change. When a substance undergoes a physical change, only its form changes. In a chemical change, both form and composition change. When the wood and copper in Figure 17 undergo a physical changes, the original wood and copper still remain after the change. When a substance undergoes a chemical change, however, the original substance is no longer present after the change. Instead, different substances are produced during the chemical change. When the wood and copper undergo chemical changes, the wood and copper have changed into new substances with new physical and chemical properties. Physical and chemical changes are used to recycle or reuse certain materials. Figure 18 discusses the importance of some of these changes in recycling. And the very last thing is the conservation of mass. During a chemical change, the form or the composition of matter changes. The particles within the matter rearrange to form new substances, but they are not destroyed, and new particles are not created. The number and type of particles remains the same. As a result, the total mass of the matter is the same before and after the physical or chemical change. This is known as the law of conservation of mass. This law can sometimes be difficult to believe, especially when the materials remaining after a chemical change might look different from those before it. In many chemical changes in which mass seems to be gained or lost, the difference is often due to a gas being given off or taken in. The difference, for example, before and after the candle in Figure 19 is burned is in the gases released into the air. If the gases could be contained in a chamber around the candle, you would see that the mass does not change. The scientist who first performed the careful experiments necessary to prove that mass is conserved was Antoine Lavoisier in the 18th century. It was Lavoisier who recognized that the mass of gases that are given off or taken from the air during a chemical change account for any differences in mass.